I'm going to start here. So finding a vector that points from here to here. There are a couple of different ways that we can do that. Really, for me, I like to just kind of think through it. So if this is my, I'm going to call it A. So this is my new vector. And when I'm thinking about that vector, I'm saying I'm standing at an x coordinate of 2, and I need to get to an x coordinate of 1. So how do I have to change? I'm going to change by reducing the x coordinate by 1. If I have to move from 3 to 1, then I've got to reduce that y coordinate by 2. And if I'm standing at 1 and I need to make it to 3, then I'm going to increase that z coordinate by 2. Now, the other way to think about this is to straight up do subtraction. So I want to go final minus initial. So I would look at those x values and do 1 minus 2. I'd look at the y values and go 1 minus 3. And I'd look at the z values and do 3 minus 1. Now notice we're going to get the same result either way, as long as we remember that in terms of doing that subtraction, it should be final minus initial. Is that we're going to think about a plane really as kind of a flat sheet. And a plane is characterized by a point and a direction. And if you think about it, that's kind of how we characterize a line also. So when we're talking about a line in 2 dimensions, like a y equals mx plus b, or a y minus y1 equals m times x minus x1, either way for both of those, I need a slope and a point. And what's a little bit different with our plane is we're going to define the direction by a vector that's normal to the plane. Normal meaning orthogonal to the plane, meaning perpendicular to or at a 90-degree angle. So if I wanted to find the equation of this plane, and I told you that the plane contains the point 1, 2, -4, and that the vector perpendicular to the plane, so here's my point on the plane, and a vector perpendicular to or normal to the plane would be the vector, let's go with -1, -2, 3. And I asked you to find the equation of this plane. Well, the way that we're going to do that is by imagining that this plane has a whole bunch of points in it. We know one of them, 1, 2, -4, but there are a lot of other points in that plane. I'm going to generically choose another point in that plane, and I'm going to call that point x, y, z. Now, I've made it really generic so that it can represent any point that's in that plane. What I'm going to do next is to draw in a vector that goes from this point that I already know is on the plane to some generic point x, y, z. So this vector right here, if I called that A, and I think about that A vector as a final minus initial, then my final x value here, we're actually just going to call x. So I'd have x minus 1, y minus 2, and z minus -4. I'm going to try to be consistent and with the notation in the book and use squared off brackets here. Sorry about that. So what I know is true is that this vector, because it lives in the plane, is perpendicular to the vector that we were given as the normal vector for this plane. If they're perpendicular, that means the dot product is 0. And I'm just going to write that down because it's super important. It's actually probably the most important thing that we remember about the dot product. So if 2 vectors are perpendicular, their dot product is 0. So to find the equation of this plane, we're actually going to take the dot product of these two vectors and force it to be equal to 0. So I'm going to look at A dotted with our normal vector and set that equal to 0. So our A vector, x minus 1, y minus 2, and I'll go ahead and switch that around to say z plus 4. We're going to do a dot product then with the vector -1, -2, 3. And force that to equal 0. With our dot product, we're going to multiply the first components together. So I would have x minus 1 times -1. Add that to multiplying our second components together, y minus 2 times -2. And add that to multiplying our third components together, z plus 4 times 3. And set that equal to 0. That is the equation of the plane. You can distribute things out, you can rearrange it, but that is all we actually need to do to write the equation of the plane. That looked like 2, 1, 3, 2, -2, 4. And I would say that the dimensions of this matrix, matrices drink RC cola, so it's rows, then columns. So I have 2 rows, 3 columns. So this is a 2 by 3 matrix. And we read that as 2 by 3, not 2 times 3. So here's my 2 by 3. 2 by 3 matrix. If we put a little t at the top of the M, that T stands for transpose. And what transpose means, the way I like visualize it, is I think about the matrix falling over. But what it actually means is that we trade rows for columns. So my first row becomes my first column. So that first row of 2, 1, 3 would become my first column for the transpose. My second row, 2, -2, 4, becomes my second column when we write the transpose. Other matrix vocabulary include things like, if I had a matrix that looked like 2, 0, 0, -4, we would call this a diagonal matrix. And it's a diagonal matrix anytime we have, so we typically call this the primary diagonal. And if we have numbers on the primary diagonal and zeros everywhere else, then we would call it diagonal. If that were, this is a 2 by 2 matrix, but if I were to like scale that up to be a 3 by 3 matrix, I might have something that looked like 1, 0, 0, 0, 3, 0, 0, 0, -2. This is also a diagonal matrix because along this diagonal, I can have numbers as long as I have zeros everywhere else. More vocabulary. If I don't have zeros up here, but instead I had numbers, now I've turned this into an upper triangular matrix. And we call it upper triangular because it's always in reference to the primary diagonal. So this diagonal that starts in the upper left-hand corner and moves to the lower right-hand corner. If we have numbers above that, then we call it upper triangular. And you could probably guess that if I had zeros here and numbers down here, we would call it lower triangular. And you would be right. Mathematicians are not very clever with naming of things. And M, we said, is a 2 by 3 matrix. And what I want to do is multiply this by a 3 by 1 matrix. And I'm going to say that's -1, 2, 1. And to compute the result, the first thing that I want to do is to know how big it is. So I check that the inside dimensions match, and they do. They're both a 3. So then the outer dimensions are going to tell me the size of the answer. So my answer will be 2 rows by 1 column. So I need space for 2 rows, but I only need 1 column. And although I'm drawing it really wide, I'm just giving myself space to put my arithmetic in. I mentioned this the other day, but when you're first starting, I find it helpful to actually like carve out the space for yourself so that you can write the locations of the pieces. And what I mean by that is this first piece is in row 1, column 1. And this second piece is in row 2, column 1. And that tells me which elements from the 2 matrices I'm going to multiply together to get the answer. So I need, for this top piece, I need row 1 from the first matrix times column 1 from the second matrix. Well, the second matrix only has 1 column. I kept it easy. So if I take row 1 times this column, I'm going to go element by element and multiply. So I'd have 2 times -1 plus 1 times 2 plus 3 times 1. When I move to the second piece, I'm multiplying row 2 from the first matrix times column 1 of the second matrix. Row 2, so I've got 2 times -1 plus -2 times 2. Again, I'm moving element by element. So -2 times 2 times 2 plus 4 times 1. And then I would probably do that arithmetic. So -2 plus a +2, that's going to 0. So I get 3. -2 plus -4. Well, -4 plus 4, that'll go to 0, and I get -2. Great. So imagine there's some population of wild dogs somewhere. That population of wild dogs has some puppies. Okay, for as many times as I've written this word, I hesitate on the spelling every time. It's juvenile? One L? Scrolling down, someone's helping me to spell. 1. Thank you. Okay. Some juvenile dogs and some adults. Now we need to make up some numbers for this population. So I will take suggestions if you have them. So how many puppies are floating around out there? And I mean, you can imagine it's a pack of wolves, African dogs, street dogs. So we got 20 puppies. That was the suggestion. So like right now we have 20 puppies. And how many juveniles do we think we've got in that imaginary pack of dogs? I can make up numbers, but cool. Let's say we have 5. Great. 5 juveniles. And let's say we got 10 adults. That's the situation right now. I've got 20 puppies, 5 juveniles, 10 adults. Now the dogs are out there and they go through a breeding cycle. And the question is, what's the population going to look like after that breeding cycle? And we got to make the parameters kind of small here. So for the moment, we're just going to think about a couple things. Well, if we go through a breeding cycle, then some time has passed. And sadly, not all of these animals are going to survive to the next breeding cycle. Also, if we've gone through a breeding cycle, new puppies. So we're really going to just take those two things into account. And one of the ways that we can do that is with something that we call a matrix diagram. So I'm going to label these as P, J, and A. So we've got our puppies, we've got our juveniles, and we've got our adults. Now, right now, there are 20 puppies. But to simplify life, I'm going to say that after a breeding cycle, they move on from being puppies to what I'm calling juveniles. The question is, what percentage of them are going to survive? I don't know. It's a harsh world out there. What percentage of the puppies do we think are going to survive to become juveniles? I know you didn't know this was participation day. 80%, great. We're just making the numbers up here, folks. So 80% of our puppies are going to survive to be juveniles. Now our juveniles, again, to keep things really simple, we're going to say that our juveniles are growing up to be adults. They're a little older, a little wiser. So these juveniles, I'm going to say 90% of them manage to survive. Oh, 10%. Ooh, harsh. People are being harsh. Okay. Okay, those juveniles, they're mischievous. They're getting into trouble. 10% of them are going to survive. Thank you. And then our adults, well, some of them are going to live another year, but not all of them. So our adults, some of them are going to survive. Now, as much as they might like, they cannot grow younger. So once you're an adult, that's it. You don't get to go back and be a juvenile or a puppy again. So these adults, they feed kind of back into the adult population. And let's say that once you're an adult, you're pretty good. You know how to find food. You can fend off predators or something. But, you know, old age, right? So let's say 70% survive. So that took care of our like survival rate piece of it. But I said there's another piece because we've gone through a breeding cycle, which means puppies. So the question is, are puppies reproductively capable? And I'm going to go with probably not. Our juveniles probably are maybe reproductively capable, but maybe they are less good at raising a pack, or maybe they're less reproductively viable. So out of like each litter from those juveniles, like how many of those puppies are going to survive, do we think? I'm going to make up a number for us. I'm going to say that each juvenile can really only handle rearing one puppy. Our adults, on the other hand, they are going to average a survival of like 4 puppies per litter. It's probably being pretty generous. Well, this diagram here, this matrix diagram, can allow us to figure out how many individuals in each of these age classes there will be after we play out one cycle of these events. So let's do it. So we started off with 20 puppies, 5 juveniles, and 10 adults. I should have done those in a different color or something, but it's okay. So if I want to know how many puppies there are next year, well, the number of puppies that there are next year depend on the number of juveniles I have this year and the number of adults. So my puppies next year, which I'm going to, well, okay, I'll just put next. So I've got a now and a next. So my next set of puppies, each of these juveniles is going to produce 1. So I'll have 1 times 5. And each of these adults is going to produce 4 new puppies. And that was 10 times, I had 10 adults and they each produced 4 new puppies. So I've got 4 times 10. Now, and that's the only way we're getting new puppies, because our puppies are going to grow up. So juveniles have puppies, adults have puppies. Now let's think about the juveniles. Well, 80% of our puppies become juveniles. And that's the only influx of new juveniles here. That's my only arrow that's coming in. So my new juveniles, that's just going to be 20 times 0.8. Now for my adults, the existing juvenile population is going to grow up to be adults. So, okay, these numbers aren't looking good, folks. 10% of 5 is half of a juvenile. Just don't think about it too hard. We made up the numbers. So for my next year adults, we're going to have 5 times that survival rate of 0.10 plus, luckily some of our adults also survive because they're not getting many from that the juveniles growing up. So of the 10 adults we have, 70% of them survived. So I've also got a 10 times 0.70. Now that got a little bit messy, but you can imagine that if we compute all of these numbers and ignore the fact that some of them will be decimals, that's 5 plus 40. So I'd have 45 puppies. 20 times 0.8. My calculator. I don't know where it is. Okay. 20 times 0.8. You would think that I could do that in my head, and I could if I wasn't thinking too hard, but I am. So 16. Thank you. 16 juveniles. And what's that? So 0.5. Again, don't think too hard about that one. Plus 7, so 7.5. So that would represent how many puppies, juveniles, and adults I had after running this through the cycle once. Well, you might imagine that biologists wouldn't just like to know what the population dynamics look like after a single breeding cycle, but they might like to know what happens after many, many, many breeding cycles. And the cool thing is we can take this and represent it as matrix multiplication. So as matrix multiplication, we can represent this matrix diagram by actually putting it into a matrix and think about multiplying that by our initial condition of puppies, juveniles, and adults, which for us was 20, 5, and 10. And if we work backwards from the matrix multiplication angle, if I think about this first row, we didn't have any numbers to multiply by the 20 because our puppies can't make new puppies. But we did multiply the 5 by the 1 because our juveniles made more puppies. And we multiplied the 10 by 4 because our adults made more puppies. Our second row, we only had a 0.8 times the 20, representing my puppies that grew up to be juveniles, but none of my juveniles got to stay juveniles, and none of my adults were able to get younger. That bottom row, my 20, didn't get multiplied by anything because as much as they might like, those puppies can't jump straight to being adults. My juveniles got multiplied by 10% because 10% of them survived to be adults. And my current number of adults got multiplied by 0.70 because 70% of them survived to live another year. Now, if we wanted to do this for a generic starting point that I will call P naught, J naught, A naught, then after one cycle, I would have the values for puppies after one cycle, juveniles after one cycle, and adults after one cycle. That imagine that we had a red blood cell or something. I don't know. Okay, so imagine that every single point in space inside of my body has a coordinate. So what problem 1 is saying is that they've administered the vaccine and the coordinates of where that vaccine have been administered was 2, 1, 0. Now, so that means here's my cool vaccine protein glob, and it was administered at a particular point. And according to the problem, it will only protect against things that are sort of inside this invisible sphere of radius 2. Anything out here, it's just too far away for this thing to interact with it. So it can only work within a radius of 2. So the question is, what if something plops in at the coordinate 0, 0, 0? Is that inside a radius of 2 from here? Well, how are we going to tell? We're going to use the distance formula. And as long as the distance between these two things is less than 2, vaccine's going to work. So let's quickly throw that in our distance formula. I am looking at the square root of 2 minus 0 squared plus 1 minus 0 squared plus 0 minus 0 squared. That is the square root of 5. Which is bigger than 2. So I'm going with, nope, vaccine's not going to work there because the vaccine is only going to work inside that bubble with a radius of 2. Now, if we kind of chopped this down and ignored the z components because they're both 0 anyway, then it's easier for me to draw. So if we ignore the z components for a second, this says that we've got this vaccine living over here at 2, 1, and we're drawing a radius, a circle with a radius of 2 around that. And I'm not great at drawing circles, but I'm going to give it my best. And visually, I think it's easier to see that 0, 0 is outside of that circle. Since these are all in 3 dimensions, and this was the only one that had a 0 for a z component, this is the only one that you might be able to draw. The rest of them, for sure, you're just going to use that distance formula and see if it's bigger than 2. The angle between let's say the vector 1, 2, 1 and 2, 0, 0. I'm making my life really easy here. If I want to find the angle between these 2 vectors, then this is going back to our primary equation for the dot product. I'll go ahead and call this one A and call this one B. And that primary equation for the dot product looks like A dotted with B is equal to the absolute value, the magnitude of A times the magnitude of B times cosine of the angle between them. So whenever we're asked to find the angle between 2 vectors, it's this angle right here in the formula that we're looking for. So just to point out, this vector that I've chosen is secretly the x-axis. If you have taken a look at WebWork Homework 8, there are questions in there that rather than giving you 2 vectors, they give you a vector and an axis. So if we're talking about the angle that a vector makes with the axis, then we can choose a vector that points along that axis and treat it the same way that we do any other angle problem. So here, this vector points in the direction of the x-axis. If I wanted a vector that pointed along the y-axis, then I could choose the vector 0, 1, 0. And that could be any number right there because it would just be a different length. If I wanted something that pointed along the z-axis, I could choose 0, 0, 1. Back to my question. So to find this angle, I'm going to do the dot product on the left-hand side by taking my component-wise multiplication. 1 times 2 plus 2 times 0 plus 1 times 0. On the right-hand side, I need my 2 lengths. So the length of A, I'm looking at the square root of 1 squared plus 2 squared plus 1 squared. And that's going to get multiplied by the length of B, 2 squared plus 0 squared plus 0 squared times cosine of the angle between them. Now it's arithmetic time. I wasn't doing so great with that on Wednesday. See if I do better today. That's a 2 and a 0 and a 0. That's 4, 5, 6, square root of 6. That's a 2. And cosine theta. So I can divide both sides by 2 and divide both sides by square root of 6. I end up with 1 divided by the square root of 6 is equal to cosine theta, which means theta is equal to cosine inverse of 1 over the square root of 6. You could throw that into a calculator. If you are doing a WebWork problem, it is important to figure out whether WebWork asked you in degrees or radians so that you make sure that when you put it in your calculator, you're in the right mode. So I believe the question in the chat is referring to when you write a vector along the y-axis or the z-axis or the x-axis. The thing that's important, it doesn't matter what number you put in, it does matter that the other parts are 0. So if I wanted something that pointed along the y-axis, one option would be the vector 0, 1, 0. But I could also choose the vector 0, 17.40. I mean, I wouldn't do that because I don't want to multiply stuff by 17.4, but it would work. It would still point along the y-axis. Cool. I think the biggest stumbling point that I feel like folks are hitting in doing these problems is this last step. You just have to be okay with shove that in a calculator and get an angle back out. There isn't a nice trig triangle thing that I'm supposed to know and have remembered for 1 over the square root of 6. We're just going to throw it in a calculator. So there is a request to do more vector practice, which I am totally up for. At 10:40, wherever else we are, I do want to talk new stuff just a little bit. So this will probably be our last vector one. And then I want to do a little bit of matrix practice so that we can get into 8.5. So if I choose something from problem 2 on the worksheet, problem 2 is kind of having us practice a bunch of different things. So let's go with, I'm looking at problem 2, part C on the worksheet, because I think it's going to let us practice several things all at once. And this has asked us to find a vector that has the same length as -2, 4, 2, and is parallel to 1, 2, 3. So there's kind of a lot going on here. For starters, if we're being asked something about the length and magnitude are interchangeable. There's another key word in here, and that's parallel. So if I have a vector and I want to construct a parallel vector, that's the same as saying take this vector and either stretch it or shrink it, but don't change the direction. So we want to preserve the direction of this vector, but use the length from this vector. So to do that, to construct that, I need to think about the length that I want times the direction that I want. But the direction piece is going to be some sort of unit vector. It's going to be, since the direction we want is parallel to this vector, I'll go ahead and call this the vector. Now let me call it A. I'm going to call this the vector A. So the direction that I'm going to use is A divided by the magnitude of A. Then to figure out the length that I want over here, the length is coming from this vector. So if I call that vector B, then I'm going to get the length from the magnitude of vector B. This isn't like some magic formula. I just wanted notation to use. It is true that when we're asked for a direction, that direction can always be given as the unit vector that points in that direction. Okay, I said can always. That was too strong of a phrase. Sometimes we're specifically asked for an angle, but if we're not asked for an angle, and like in this case, we're just trying to construct a new vector, we're going to construct it by having a length times a direction. So our length here would look like the square root of -2 squared plus 4 squared plus 2 squared. And our direction would look like that vector, 1, 2, 3, but with each term divided by the length of the vector. So I need the magnitude or the length of A, 1 squared plus 2 squared plus 3 squared, 1 plus 4, I'm at 5, plus 9, square root of 14. If you clean up that number and distribute it in, that would be my final vector for that. And kind of everything in problem 2 is sort of variations on that theme. So saying that we point parallel to this is the same as saying we point in the same direction. So like A, B, and C of problem 2 can all kind of be treated the same way. We need to figure out what's the length they're asking us to use and what's the direction they're asking us to use. Oh, I wouldn't leave it like this. I would do the rest of the math. So what's that? 4 plus 16, so 24. So that's square root of 24. And then I would distribute that in. So I would have square root of 24 over square root of 14. 2 square roots of 24 over the square root of 14. And 3 square roots of 24 over the square root of 14. And I'm sure there's something you could do to simplify that further if you really wanted to.